Anyhow, the two important things we got to talk about right now. The exam one, I'll post it tomorrow at the latest at noon. It'll be due Wednesday at 11:59. It'll look similar to the homework problems. And then just to give you a better idea what you're going to get, I'll post an exam, an old one for you on Canvas after class. And so if you're keeping score at home with things like you're reading the book and all that, hopefully you are. So the exam covers chapters 1 and then 3 through 5. So up through fluids. So what I'll be testing you on are, I mean, what's fair game is a better way of saying it. Fair game is anything we've done for homework and problems that are very similar. Fair game is any problem that's in the textbook or something similar. So when I say something similar is, I mean, when you get this test on and look at it tomorrow, all the problems might look familiar. They might look identical to something you've already done. And even if they don't look, just like it, then there's a high chance that they're very similar to what we've already done. Now, you guys, I don't think there's any questions. Although you guys, some of you might be interested in your grades. I didn't update them yet. I guess I'll try to do that before the test. Maybe today. I can't guarantee that though, and I apologize. But no one's in jeopardy of any issues right now, grade-wise. Anyhow, so if you're concerned about something with your grade, shoot me a personal email, and not personal email, but email me, and we can discuss that in detail if that's something you're concerned about. But I usually tell students, you don't need to worry about your grade until after this test, and then we'll figure everything out from there. So, okay, so does anybody have a question about the exam or a comment, complaint? Do you want it earlier? I mean, so I'm assuming some of you might email and say, can we have it tonight? I don't know. Does anybody have a question or a general comment about the test or the course? I mean, you don't have to. I'm just curious. Okay, so there's a few more things that we should say about fluids, and that's what we're going to do now. Any questions about homework problems, by the way? So hopefully the lack of questions means that you guys will all perform admirably on the first exam. Oh, by the way, I meant to say, I got an email from Dr. McCarthy, and she wanted me to, I guess there's a recruiter that wants to meet with you guys. If anybody said anything to you guys about this?
No.
No? Okay, so next Monday at 10 o'clock, a woman named Maddie, I believe is her name. I should have looked up the email, but she's going to join us at 10 for a moment or two. And I think I'll have to double check. But I believe she's with UPMC, or maybe she's with Allegheny Health Network. But I think she's a recruiter to talk to you guys about jobs and stuff. So I don't know if anybody said anything to you about it, but if not, and then you're hearing it first from me, let me actually double check with the email so I don't misspeak. If you bear with me. So make sure you're here Monday at 10, and make sure everybody knows that that's the case. Here, yes, Maddie. So she's with Highmark and Allegheny Health Network. So Monday the 29th, her name is Maddie Hudak, I think. And she's the campus and community program specialist. And her and Marie Kelly. I don't know either one of them other than emails. And they will be joining the party for a little bit. So I don't know if you want to dress. I don't know what the whole purpose of it is. I think it's just a meet and greet type thing. I'm scrolling through 400 emails to see. Somewhere along the line, I got forwarded into these communications. So now you know. Yeah, so I'm not exactly sure what the part. I can't get to the some of the earlier emails. It says Allegheny Health Network's CRNA recruitment event. So I guess this was supposed to be something that was going to happen in person in April. I don't know if you guys know anything about this, but now you know. So they're going to join, and so maybe make sure you're here. Smile. Wear your Sunday's best. I might even put a nice shirt on for this party. Okay, anyhow, enough killing time. So if you guys have any questions about what that might be, maybe, shoot me an email and I can dig deeper. I can talk to Dr. McCarthy and let you guys know. But spread the word to all the peeps, because right now I see there's 10 of you, including me, so half of you are sleeping. So make sure everybody knows that Monday, be here if you can. All right. Anyhow, good. Let's do physics. Something's still in my eye. I can't see. This is terrible. This is not ideal. Okay, so good. So let's get started so we can finish, because the sooner you start, the sooner we're done. So what we've been doing is we've been studying fluids. And at the end of last class, look, so we did, we spent some time last class doing some math, which you probably don't like, but that's part of physics. And we did some algebra, and we sort of derived some important formulas. This equation of continuity, and then we talked about this Bernoulli equation. These are things that you should know. Like when you hear the English words equation of continuity, you should know what that means algebraically, formula-wise. If you hear a Bernoulli equation, you should know what that means. And if I can give you a caution, these are sort of concepts that if you go to the Google machine and start Googling these, that's not a bad thing, but you're going to likely see more general statements of these that might not be as easy to understand. Is sort of I hate to use the way, but it's true. We're dealing with simplified versions of more complicated ideas. And I've alluded to this before. I said we're simplifying these things so that we can use algebra to sort of do deductive arguments and derive things. And if you want to derive more general statements, you often need to use more higher level mathematics, but we're not asking you to know that stuff. So I would caution you to, if you want to think about the equation of continuity, think about it in the context of how we did it in lecture. Now, I'm not telling you not to go look on the internet and stuff, but you're likely to find things that are not so simplified. In fact, I'm interested to see what happens when I do that right now. So I will go to the internet machine and I will Google equation of continuity. And I get things in fluid mechanics. And some of these pictures look simple, but some of them look much more complicated. So what I would encourage you to do is I would encourage you to be careful of how you peruse the internet. Because one of the things, I don't want to say that this, I always found this weird. When I was a student, it didn't matter because there wasn't all these resources available to you. But I'll have students tell me that instructors will tell them they should be careful and not use the internet for things and Wikipedia. And I got to be honest, I think that's one of the I don't want to use the word dumb, but to me, it's a dumb piece of advice. I mean, Wikipedia is sourced. So you can get things from Wikipedia. You can Google, I can Google journals and high-level math research and physics research. So this whole thing that people tell you and you can't get information from the internet or you can't trust it. Well, I guess in some aspects they're right, but in other aspects, one of the best ways to learn physics is to use all the resources that are on the internet, the videos, the solved problems, go to YouTube. I mean, that's one of the easiest and most beneficial, resources you have. And so I hope that you do use that, but I also hope you use our notes, and I hope you use the text, because it is, you do have to be careful when you start getting in some of these things on the internet. You might run into more general statements of formulas, and the equations might be a little more overwhelming than you expect. So just keep that in mind. Yeah, so like if I Google the Bernoulli equation, I get this nice little NASA funded picture. So anyhow, Google search at your own peril. No. Anyhow, that's what we've been studying, fluids. So, and of course, there's two types that we'll study. We study static, that's non-moving fluids, and then of course moving fluids. So that's hydrostatics and then hydrodynamics. All right, so I think the last equation we stated, and I asked you to sort of analyze this on the homework. So hopefully you guys will do that for me and for yourselves. Is we introduce this idea of that in the simplest situations, we never considered friction. We just imagined fluid moving through a pipe, and there was nothing to it other than we had fluids moving, and we would first look at pressure, and then we might look at how it's moving, speed, or how much of it is moving, the flow rate. But what we find soon enough is if we want to be more realistic, if we want our equations to be much more valuable, that is, if we do an experiment, does the mathematics match the experiment? Are our equations accurate? Do they predict experiments? So if we want to be more accurate to what we see in an experiment or what we see in the real world, we have to account for friction. And then what friction does is that gives us this new quantity that is of importance called viscosity. And so we end up getting this very pretty formula. And let's remind ourselves what it is. So again, I forget the correct way of spelling or pronouncing who's willies or whatever. I don't know. Perhaps I should take the time to research that so I can properly say it. Maybe you guys have heard of this name before. I don't know. But anyhow, what is it? It's usually stated like this. Your flow rate is the ratio of the pressure difference times pi times r to the fourth over 8 eta L. And remember, this eta is, let me write that a little cleaner. Eta is the viscosity. L is the length. And remember, we're assuming we have this cylindrical pipe. So R is the radius of the pipe. L is the length. P1 minus P2 is the pressure difference at other end, or at either end of the particular pipe. And let's put a little box around it in red. That looks so pretty. Now we could also write this term, or excuse me, this instead of flow rate, we could, we could find other descriptions of this formula, but this is typically the one that we use. Now, of course, we know flow rate is in a cylindrical pipe is related to its velocity times its area. We talked about that last class, so you can get that involved. There's different ways that you can write this particular equation. So one of the homework problems is asking you to examine this. What happens when P1 minus P2 changes? What happens if R becomes larger or smaller? What happens with L? How does that affect pressure? How does that affect speed? And again, one of the things I kept sort of hammering on last class was we can get simple equations to describe how quantities are related, or more generally, we want equations that describe some sort of physical thing. Like, one of the things that I was mentioning is we were talking about buoyancy. How do things float? And so we talked about how, okay, we can get equations to understand what forces or pressures are acting on an object that's submerged. But the idea is we want to write the equations in a way that they are intuitively useful to us. So that by looking at the equation, we can say, aha, I get it. If density goes up or down, then we would expect you to float versus sink, or vice versa. And so when we write, this equation in the red box that we have here, when we write it like this, we want to be able to use our sort of numerical sense, our sense of how numbers work, fractions. We know that when we divide something by a large number, the whole thing becomes smaller, and vice versa. And so when we have these basics, sort of intuitive ideas of how numbers behave, then we can actually see by looking at this equation. I mean, this is sort of the goal that you want to set for yourself, the barometer, if we want to make a pun about this class. If you want to sort of have, a little test in your own head about how do you understand sort of, I should say how do we understand, but you imagine you see some physical thing, you're in a hospital room, and you realize that if you have an IV and you change the tube, that it's the length of the tube, how does that affect things like flow rate? How much medicine is being distributed per hour? Or if you change the radius of a tube, what does that happen? How does pressure become involved? So these are the kinds of things that I would encourage you to think about, not just this concoction of symbols, but when you're looking at this concoction of symbols that is likely overwhelming to many of us who aren't huge fans of math and physics. But to think about these symbols in a real setting. I'm not suggesting that it's easy to do this all the time, but it is something that you know, it could be worth your while. Okay, does anybody have a question about this? All right. Good. All right, I lost my cursor. I always lose my cursor because I have a couple screens working here, and then you can't find the mouse cursor. Oh, I dropped my water. All right. All right. So one last thing we're going to say about fluid moving through a cylindrical pipe. And okay, let me also remind you, this bears worth repeating. Why do we keep dealing with cylindrical pipes? Well, most important reason is from a mathematical standpoint, they have simple geometry, and that's useful. And then the next important thing, at least if we're trying to develop things that help us in the real world, is that a cylindrical pipe is a good model for many things that we encounter. For example, in the situation that you guys are interested in, as say from a nursing perspective or an anesthesia, imagine we have tubes that we're giving, you know, fluids and gases. Those are, you know, they are cylindrical pipes, hoses. And even things that aren't necessarily cylindrical, like, you know, blood moving through your body, we can use a cylinder as a sort of glorified, simplified model of our, you know, arteries or our, you know, our veins, our blood, how it moves. So, you know, oftentimes you might get bogged down by saying this isn't realistic, or you might say, why do we keep studying cylinders? Well, there's two different reasons you might want to remind yourself of as we do this. Okay, so the last thing that we should mention about fluid moving through a pipe, as it were, is what's called the Reynolds number. So the last thing we're going to say about fluids is what's called the Reynolds number. So let's just write down what it is by definition, and then we'll talk about it briefly. So it's usually denoted N sub R. And it's 2R rho V over eta. So again, we're using context here. We're imagining we have a cylindrical pipe with cross-sectional area pi r squared. And so R is the radius. I guess I should be consistent. Let me fix this V. That looks like it could be volume. This is our velocity. So you remember for velocity, we've been using this little lowercase script v. I'm writing it again. I must have stroked out over the weekend. And then, of course, eta is the viscosity. And then last but not least, rho is the density of the fluid. I guess, okay, let's be a little more perhaps I should write this a little better. I shouldn't say velocity of the fluid. Let's say average speed. So why do we introduce this number? It just turns out that what we found through experiment and through studying is that this sort of relationship, this ratio, is useful in describing how we can characterize fluids. One thing you might notice that I didn't state this, but I've mentioned this kind of stuff enough. If you think about what units we're using here, there are no dimensions to this number. All the units cancel out. So that makes it useful as well when we're trying to discuss the characteristics of a specific fluid. Does anybody have a question about this? So you might say, well, what characteristics do you mean? Well, what the Reynolds number gives us is it gives us sort of a decent gauge of when we're going to have certain types of flow. Well, we have laminar flow, which is nice and sort of, like we said, has some sort of, I want to say symmetry, that's a bad word, but a nice smooth flow. Or if the Reynolds number tends to be at a certain level, that means that we're likely to have turbulent flow, very chaotic flow. It's not smooth. Again, we're using an equation to sort of give us a way of characterizing how we expect or what we expect to see in a real world situation and or an experiment. So if you look at this equation, you notice that you're dividing by this viscosity. So then you can do things like, okay, if the radius is small and the speed is something, well, what if the viscosity is large, whatever that means? Well, that means the Reynolds number, we would imagine, would be small. You take a number and divide it by something large, whatever large is. Or another way of saying that is if the numerator is small compared to the denominator, then you have a very small Reynolds number. If you have the numerator is being large compared to the denominator, then you have a, quote unquote, large Reynolds number. And then if you think about what those letters mean in the numerator and what the letters, or the letter in the denominator mean, what those variables represent, then you get an idea of how, think about your intuition, how you would think fluids move. I mean, what sort of situation is likely to have, say, turbulent or very unsteady flow, a small pipe where the fluid's moving slow, or a large pipe where the fluid's moving fast. So if you think about these scenarios and how these letters sort of play, you can, in many ways, instead of memorizing these formulas, they become second nature if you think about what your intuition tells you about flow. Okay. Any questions? Okay, so Reynolds number, a good way for you to think about its use is it's a number that helps us sort of characterize if we expect to have laminar flow or turbulent flow. And now, don't forget, everything that we did about moving fluids in this particular class was about laminar flow, which is a steady, smooth flow. The study of turbulent flow is a very complicated thing. And we're not even going to begin to touch on that. All right. And by the way, this number can be used in other settings. It doesn't just have to be a cylindrical pipe. And let me check it out. The Wikipedia page for Reynolds. I'll see the Wikipedia page for the Reynolds number is nice. You can read it. You might learn something. Oh yeah, okay, yeah. Yeah, there you go. All right, very good. Does anybody have a question, comment about homework problems? So while it's on my mind, what I'm going to do right now is I'm going to go to Canvas, and I'm going to give you guys a gift. So let's go to assignments. And I'm going to upload an old exam for you. And what I would encourage you to do, I don't think you're going to find it difficult, to be completely honest. I don't think so, at least, is what is happening here. What I would encourage you to do is check this out, even if hopefully you can do it right now, and see how, the exam's not going to look exactly like this, but you would imagine it's going to be quite similar. And let me see, is it there? Yep. There you go. So I posted, if you go under your assignments, you'll see it says old exam for practice. Check it out. That's the one I gave last summer. I don't know if there was fluid stuff on this one. There will be fluid stuff on ours, but check it out, see what you think. Hopefully you can solve all the problems relatively easy. Well, I shouldn't say it doesn't make any sense, but they all seem to be relatively easy for you. So I would tell you to work on that. And if you have questions, let me know. I can post solutions if you want. Does anybody have questions about the exam or that kind of stuff? Going once, homework. All right, well then why don't we call it that. What I'll do is I will let you know when the exam is posted sometime between now and noon tomorrow at the latest, and then you guys can go from there. Any questions, comments? Be happy to stick around and answer any questions if you want. Otherwise, I say thank you, and I will remember no class Wednesday either. Don't forget that. And so please spread the word, no class Wednesday, and then also spread the word that Monday we will have recruiters coming to Zoom to talk to you about whatever, jobs, I don't know. Maybe they want to hire you. Maybe you already have a job, I don't know. All right, so if you guys don't have questions or comments, I say Godspeed, and I will talk to you all on Monday at 9 a.m. So you know on Monday will be at least an hour because we're going to have visitors at 10. All right. I will talk to you guys. Have a good one. Good luck on any exams you have. And thank you for joining in the party. I will talk to you guys later. Thank you guys.
Yeah.
Thank you.
Thank you. See you later.